The metric system and scaling. Scaling is how characteristics change when you change size. The metric system is based on the meter, on the liter, and on the kilogram, which is the mass of 1 liter of water. Okay, let's know our prefixes. A meter is equal to 10 decimeters, so deci is 1/10. A meter is equal to 100 centimeters, centi is 100th. And it's equal to 1,000 millimeters, the width of a dime. A millimeter, milli is 1,000th. Okay, so where did the meter come from? Originally, when we look at the Earth, we define the meter as 1/10,000,000th the distance from the North Pole to the equator along a meridian. So this distance was defined as 10,000 kilometers. Kilo is 1,000, so that's 10 million, or 10 to the 7th meters. A meter is 1/10,000,000th the distance from the pole to the equator along a meridian. This also gives us a good idea that the circumference of the Earth is equal to 4 times 10 to the 7th, or 40 million meters. Volume. So what is a liter? A liter is a cubic decimeter. So we take a decimeter, 1/10 of a meter, in height, in width, and in depth. And we have a liter. So 1 liter is equal to 1 decimeter, 0.1 meters cubed. And so we look, this is my 1 liter of yogurt. About 1 liter of yogurt is 1 decimeter cubed of yogurt. The unit of mass, the kilogram, is defined as the mass of 1 liter of water. About the same as the mass of 1 liter of yogurt. A kilogram is the mass of 1 liter of H2O. Okay, what is this in empirical units? This is about 2.2 pounds. Okay, however, now we have a problem, because this is a unit of mass, how much substance there is in something, and this is a unit of force. Right, so 2.2 pounds is actually the force of gravity acting on 1 kilogram of water. So the kilogram of water is the mass that I have. 2.2 pounds would be the force of gravity acting on it. But hold on. Newton told us that force is equal to mass times acceleration. And weight is the force due to gravity pulling on something. And so if you drop something, it accelerates with gravitational acceleration, and so the weight must be equal to the mass times the acceleration of gravity, which we estimate it's 9.81 meters per second squared. In this class, we'll always estimate it at about 10 meters per second squared. So the weight of 1 kilogram in metric units is just that 1 kilogram mass times the acceleration of gravity of 10 meters per second squared is 10 kilogram meters per second squared, 10 newtons. So rather than say 1 kilogram is 2.2 pounds, we can now say the force of gravity on 1 kilogram, the weight of that 1 kilogram is 10 newtons, is about 2.2 pounds. Okay, so let's take a look at scaling. What happens as we make objects bigger? So for instance, a liter is 1 cubic decimeter, or 1/10 of a meter cubed. How about if we had 1 meter cubed, a cubic meter of water? What would that mass be? What would its volume be? And we might say, oh, well, there's 10 decimeters in a meter, so a cubic meter would have 10 liters. We could say that, but we'd be really, really wrong. Why? Because if we look at cubic meter, it would be 10 units high, it would be 10 units wide, and it would be 10 units deep. So we'd have 10 of these times 10 high, that would be 100. So the surface area would grow by a factor of the length squared. It'd be 100 times the surface area, plus it would be 10 units deep. So it'd be 10 times 10 times 10, or 1,000. So we can write then that a liter is then equal to, oh, we have it here already. We could just carry that out, and this is 10 to the negative 3 meters cubed. Right? So the key is you have to cube the decimeter as well when you get volume. So a cubic meter is 1,000 liters, and therefore a cubic meter of water would have the mass of 1,000 liters, or 1,000 kilograms. So the mass of a cubic meter of water would be 1,000 kilograms, or 1 metric ton. Similarly, if we wanted to get the mass of 1 cubic centimeter, maybe this will be more visible, we would have 10 of these cubic centimeters along here, 100 in the whole face, and then another 10 of these faces all the way back. So it would be 1,000 cubic centimeters in 1 kilogram. And therefore its mass would be 1,000th of a kilogram, or just a gram. And maybe you've heard the density of water is equal to 1 gram per cubic centimeter, or 1 kilogram per liter, or cubic decimeter, or 1 ton, 10 to the 3rd kilograms per cubic meter. So this scaling has profound effects on how biological systems can survive and why we're built the way we are. Okay, so what we see is that mass, and therefore your weight, mass is proportional to volume, how much substance you have, how much water we have, and that's proportional to length cubed. But your surface area is proportional to length squared. Why is this important? Because if we look at two animals, so we have animal A, looks like this, and animal B is twice the size of animal A, twice as high, and twice as deep. Okay, so it's pretty clear that the mass of B is equal to the length cubed, or the mass of B is proportional to the length cubed, so the mass of B is equal to 2 times 2 times 2, 2 cubed times the mass of A, or 8 times the mass of A. But how about the strength? Is the strength also proportional to 8 times? And it's not, because the strength of our arms is proportional to, if you chop the muscle, the cross-sectional surface area of that muscle is proportional to the number of muscle fibers. So strength is proportional to the area, right? And when we talk about the area, we mean the area of this surface. So this can be the area of muscle fibers that are contracting to do pull-ups, or the area of bone that are supporting the structure against the force of gravity. And so the strength of B is proportional to the area of B, which is 2 squared times the strength of A, which is equal to 4 times the strength of A. So as things get bigger, their mass grows faster than their strength to support that mass. And that's why, for instance, when you look at insects, they stand on little pinnacles. You have a spider standing on little tiny pinnacles, and they can jump many times their height. But you look at an elephant, elephants look like this, with these huge pillars, like cement pillars holding up their bodies. Or you can compare the skeleton of an elephant with the skeleton of a cat. And they're very, very different in the way they're shaped, because a cat has much greater strength for its size than an elephant does. So elephants are built with very, very large bones to support that extra weight, and cats can be built very thin and great for jumping. And ultimately, an elephant can't get any bigger, or there'd be bigger animals. So in order to be a bigger animal, we'd have to be supported by water, which is why the largest beasts on the planet are whales that can swim, because they're supported, because their skeletons don't have to support their weight against gravity. All right, there you go. Thanks.